Hello viewers, and welcome to this video, this STM32 tutorial video. In the last video, I was playing around with pulse width modulation, and I was running 4 PWM channels, each following a sine, an individual sine wave. And I mentioned that I would probably be done with and be done with LEDs and pulse width modulation and move on to UARTs. However, as usual, I changed my mind a bit. Again, I'm running this fairly unscripted, so it is more what I feel like than um, following a specific plan. Now, since we were using sine wave, sine calculation in the last video, I thought, why not look at the digital to analog converters that are built into the STM32. So if we look at the data sheet for the STM32F405 that we are using, you will see that it contains two 12-bit digital to analog converters. They are described like this in the datasheet. So two 12-bit buffered digital to analog channels that can be used to convert two digital channels into two analog voltage signal outputs. And there's a bit of a description here. If we look at the block diagram of the STM32F405, you can see that the digital analog converters are hanging down here of the APB1 bus. And well, today we will try to run a sine curve on one of these DACs. So let's dive right into it. As usual, I have started a new project here, which I call STM32 World DAC1. I have added our usual stuff with a tick statement printed in the loop so I can follow what is going on. And if we try to run this, we have the serial output here, and you can see it's counting and it's running about 12 million loops each second. It's running through the loop 12 million, roughly 12 million times. So let's look at the configuration. Now, if we look at the DAC in the configuration setting here, we can enable our out1 configuration. And you will see down here that we can enable or disable an output buffer. An output buffer basically means it can drive more current. If we don't have the output buffer, the output will be slightly more precise, but if we draw any current whatsoever from that the GPIO pin, it will be wrong. It can't do that. So for now, we are not really interested in precision. So let's just enable our output buffer. And we'll see you have a trigger down here. The way the digital analog converter is, you have a digital value and then you trigger a conversion, they call it. And when you convert it, it results in an analog output on the specific pin. Let's look at this, by the way. It is using the PA4, and if we look at our device, I have actually now connected the oscilloscope to that particular pin. So we can trigger this in a number of ways. We can use a software trigger and we can trigger it from a timer. Now, in this case, if we want to create a sine wave on it, we need a specific sampling rate, so to speak, a specific interval between each sample. So let's before we even start configuring this, let's look at the timers, and we noticed we could use, for example, timer 6. So let's go down and configure timer 6. We activate timer 6, and we want this timer 6 to run at a well-known sampling rate. Now, in the clock configuration, you can see that our APB1 timer clock is running at 84 megahertz. So for convenience, because my math is not very good, let's start by pre-scaling that by 84. We do 84 minus 1. That means we get down to a 1 megahertz immediately, right away. Now, if we want to go down, say, for example, to 10 kilohertz, we can divide this further by 100. So divide by 100 more minus 1. And we need to send an update event whenever that happens. Now, once this timer is started, it would just keep running. It will count up from 0 to, it will divide with, so at 1 megahertz, it will count up from 0 to 99, and then next time it will go back to 0. And that is how that works. Now, for now, just to test that the timer is working, let's enable the global interrupt for this timer channel, and let's try to generate our code. Now, the first thing we need to do is we need to start our timer, and we can do that as usual. I have cheated a little, so I don't have to make this up. After we have started down here, let's fire up our timer. So we simply start our STM32 timer 6 and with an interrupt. So let's do the interrupt callback handler. I have that somewhere as well. So we can go up here and add a callback, and that is the held time period elapsed callback. And we need to check that it is our STM6, and then we update a callback counter. So let's go up and create that as a private variable, and that will also be a we call it C, and we start with 0. And in our loop down here, we can then print the CB equals and print our callback counter. Let's try to run this. Here we have the output. So we can see that this callback, as we predicted, will run at 10 kilohertz. Now, we could make this much faster if we wanted. Let's just experimentally try that. We could set this to 10 minus 1 instead. Generate the code. And run the code. So now we get about 100,000 of these every second of these interrupts. But let's go back to our 10 kilohertz timer frequency. So there we have that. So now let's go up to our DAC configuration again and say we want to trigger this from our timer 6 trigger out event, and that means the timer will, the digital analog converter, the DAC, will convert one value every 10,000 times every second. Now, it would be quite hard to keep up with having to feed these values into the DAC. So what you will typically do for this is we will use DMA, direct memory access. DMA is basically a process that runs outside the core, and it's a stream, and it will move data from the memory to the peripheral. This will happen automatically every time the DAC needs a new value. It will fetch it from the DMA stream. Now, we can run these DMA in different modes, but we will run it as a circular buffer. That means that it will eat all these values, and then it will start all over again and keep doing it. Notice that the data width for the peripheral is a half a word, that is 16-bit, and we might as well use 16-bit as well in our memory. So we now have that configured. Let's, as usual, we generate our code and have a look at this. Now we need some extra stuff to make this work. What we need is, I will define a few, I'll create a few defines that we'll get back to later. So up here for the private defines. Now I want a DMA buffer size. This is a buffer that the DMA is using to feed data into it. I'll also define our sample frequency, which was 10,000. We have already verified that. Now the DAC, remember it was a 12-bit DAC, so that is 4096 different values. Since this goes from 0 to 4096, but we want a sine wave, within that we need the midpoint of that output range. That's 2048. That was just a few variables that we need. So we can now go down to the variables and we can create our DMA buffer, which will look something like this. Notice I am setting the buffer to 2 times the DMA buffer size. The reason for that is when you're using a circular buffer like we did in the settings in here, remember it was a circular buffer, then that buffer is handled in 2 halves. So it'll do the first half, then it'll fire and interrupt, and that means that while it is using the second half, we can modify the first half, and vice versa. When it's fully done, it will start using the start of the buffer, and we can use the second part of the buffer. We now have that buffer, and that means that we can start our DAC, and that is done like this. We have to start the timer first, and then we start our DAC. Look, it has a handler. It is using DAC channel 1. It is serving a pointer to our DMA buffer, which we just created. The sample size is 2 times that DMA buffer, and it have an alignment. Just believe me for that. I'm not going to go into details while it is like that. Now, let's go in again here and look at the interrupt settings for this. You'll see that it automatically have created a interrupt for the DMA stream, and that we can use in our code by using a couple of callbacks. So let's create these callbacks up here. Again, I have cheated a bit, so let's not worry about that for now, and let's not worry about that. We'll just update some variables so we can see that this actually works as we intended. So we need to create these CB half and CB full. So UN32T CB full equals CB half equals 0. So every time the buffer is half used, that means the buffer size is gone to buffer size. It will increase this one, and every time it's fully done, it will increase this one. That is how those callback works. Let's print out that stuff. So we have we do half and full. Full. Here we go. Now, what are we expecting here? We are expecting our callback, our interrupt callback, to run at 10 kilohertz, and we would expect these to run divided by 32, since our buffer size was defined as 32. Let's try to run that and see if the numbers make sense. Here we have our output. So approximately 10,000, and do we have a, let me fire up a calculator. I can't do that in my head. 10,000 divided by 32 is roughly 312, and look what we have here. Well, it's actually half. That's odd. 150. It should be approximately. What did I do wrong here? Did I? So 10,000. That's a little bit odd, but let me worry about that later. Now you see what I actually did in the stuff I prepared. I have this DAC because the calculation when the buffer is half true and when the buffer is full true is the same. It's just we put the data in a different location. So when we're half true, the DMA will start using the second half of the buffer, and that means we can play around with the first half of the buffer. When the conversion, when the buffer is fully used, then it will start using the first part of the buffer, and that means we can modify the second half of the buffer. So let's create the DAC like this. That means it will be called, and in here what we need to do is we need to fill up the buffer. So we do something like this. We can use the buffer size, right? We have the buffer is, the complete buffer is twice the size of this buffer size defined. So we basically need to go through it, and then we need to give them some value. For now, just to play around with it, let's try to do buffer I equals, I will go up to 32. So if we say I multiplied by 3200, that should be 3200. It should be visible. Let's try to do it as simple as it and see what happens. Well, it's definitely running. Let's look at our scope. Device there. So you can see we are now filling this buffer up. So every time you see one of these, that is one of those callbacks that has filled up the buffer. Of course, we don't want to do a triangular wave. So let's start to do a little more math. But this is just to prove that the DMA is indeed working as we expected. It takes data from the buffer and it pumps it out at a known frequency to our DMA, to our DAC. Sorry. So, I have prepared this calculation so it will look something like this. So let me go through what happens. We need some variables defined. So let's do these variables up here. There. So we basically have an angle. This is exactly like we did in the PWM video, and then we have an angle change, and the angle change is basically based on our sample frequency, which is 10 kilohertz. So it's 2 pi's divided by our sample frequency. That is the angle change for each step around the unit circle. I thought I needed. I am also going to add one more variable for convenience, and that will be a constant. Can add it up here, which is the value of 2 pi, the entire circle. You can see if we go down our calculation. So we basically take each of these. We take the midpoint, which started at 2048. We don't have that yet. And then we take the output multiplied by cosine from the angle, and then we update the angle. If the angle gets bigger than our 2 pi, then we subtract 2 pi from the angle. So we keep it within 0 to 2 pi at all times. Let's try to run this. There was an error. What was that error? Up here. Oh, sorry. We need a library. We need to include math H. Now I think it'll build. Yep, it built. And we run it. Let's see what happens. So it is definitely running. Let's look at the device output. And there you see a beautiful sine curve. And if we look at the frequency, it is 100 hertz. Now, if we look, oops, sorry, I need to remove that one. Look at where we defined this angle change, we set it to 100. So if we set this to 1000, it should run at 1 kilohertz. Let's try that. And let's see our device. And you will see I can change the time base a bit here, and you can see it is there. Now you will notice that this doesn't look like a curve anymore, and that is simply because these steps is our sample rate. This is how often we have new samples, so we could try to up that sample rate a bit. Let's try for fun to set the sample rate to 50,000 rather than 10,000. How do we do this in here? We need to go in here in the timer. Now, if we set this, right now it's 10. If we set that to, so we basically need 1 million divided by 50,000. That is 20. So we need to set this to 20 minus 1. Let's try to do that. I don't want the cancel project generate code. Let's see how that looks. Oh, you missed completely. My fault. You'll see now it is actually relatively smooth at 1 kilohertz. What I did before when I actually covered this, I merely changed our timer counter reload here. So now it is running at the sample rate is 50 kilohertz and our frequency at 1000 looks relatively smooth. If we zoom in, you'll see that there are still some steps there. So if you want this to be even smoother, let's try to up this value to 100 kilohertz. And I am doing this because now something interesting is going to happen. Oh, so again, I forgot to remove that. So I updated the frequency to 100. And that means we need 10 in here. So we need to count actually 9, but that's so 10. And we try to generate code. And we try to run it. Now something relatively interesting is going to happen. Here, we get the starting, but we don't get the tick anymore. Strangely enough, it's also failing a bit there. Something really weird is happening. Now, what is happening in fact here is that this interrupt now have become so quick it can't be handled. Now, if we this calculation simply takes too long. We can actually see this if we go in and we do run with debugging. Let's try to run the debugger here. We need to have the statistical profiling, and we need to resume this and run for a little while and then pause, and you will see that it is spending an enormous amount of time doing math. It doesn't really have time to run our main loop anymore, do DAC. It doesn't have time to do it. So what can we do about that? We need to come up with a more efficient way of calculating our function. Fortunately, ST have provided us with an excellent way of doing this. If we go into CubeMX again and we go into software packs and select components, I have probably already selected it. You'll see under ARM CMSIS there is a DSP library, and we have included this DSP library in our code. I am not sure whether we had enabled it, but it will show up down here on the middleware, and we have the CMSIS, and we have actually included it. So that means we can optimize this calculation quite a lot. The ARM CMSIS library contains a much more efficient function. Rather than COS, we can use the ARM COS F32. That is much quicker. So if we try to build this, we at least we get a warning because we haven't included the library. So let's include the library as well. A header file, header file. So we go up here and we include ARM math. Let's build this project, no warnings. Let's flash it and let's see if we got our output back. Our SysTech timer, yes we did. So we get about 1500 callbacks. Let's see how it looks now. Sine, perfect sine wave. So let's try for fun to do a little profiling on this one and see how, no, let's first look at, you'll see that it actually still goes through the idle loop 10 million times roughly. So it's got plenty of time now. We could actually probably up this to 200. I'm saying that, let me try it. So let's try to see if we could actually run it at 200 kilohertz. 200 kilohertz. I've honestly, I have not tried this, but I suspect that it could actually work. So let's change the timer to 5. 5 minus 1. That's only 4. Let's see. Generate code. Let's try to run that. We should see that we get much more of these interrupts now. Well, it works. 3000, so we get a lot of interrupts. Notice another thing that we could optimize a little bit here is we really don't need that interrupt. We don't need the timer interrupt anymore. So we can go into here and we can remove this. So now the global interrupt is not enabled on the timer, and you will see that we now don't get this callback called anymore. So we save some performance there, but everything else runs exactly. And again, I missed actually showing you what I was doing. I was just going in here and I was removing the timer interrupt. I also need, no, I have updated this. So now we are running this at a sample rate of 200 kilohertz. And if we look at this one, and you'll see that that is absolutely perfectly smooth. So we get a very nice curve. One thing you'll notice if you look carefully is you see it looks a bit weird up in the top and down at the bottom. What is happening there is that we put this mid to 24. So if this value actually is 1, the result of this, we end up with 4096, which is 1 too big. And that is why you could add an amplifier to make this a little stay within the range. So we do another float amplifier equals 0.9. Now we don't get the full range, but it should look a lot prettier. Let's try to build and compile that, and first we verify that it is running, and it is. Now let's look at how it looks. Let's do the big one. There, you see now it is perfectly smooth. It's no longer going through it's not clipping, is the technical term for it. So it stays within range, but you will notice that the lower part is now no longer going down to 0. It is, and it is not going up to 3.3. It is staying within another range. So we are now running sample height. Oh yeah, this is what I wanted to do. Let's look at I mean, first of all, while it's running, you see it's got plenty of time spending in the loop. Let's try to profile this. So let's run the debugger again. Let's let that run for a while, and then we look at the statistical profiling. We pause here, and you will see that it is spending most of its time in the main loop, but a little bit of time in the ARM COS F32. Now, an interesting observation here is that the DAC, which is the function we are calling up here is spending less time than just calling this function. So it is quite obvious that the expensive part is calculating the cosine. There are all kinds of tricks we could use to optimize that. Lookup tables is a typical one, but they take some space and it's not really necessary. I think we have proven our point. We can run at a 200 kilohertz sample rate. I think we could probably go up to 500 kilohertz, but I'm not going to bother with that. Now, I think this video is probably long enough. I apologize for I made a few mistakes. I have actually started playing around with putting my face here, but it still doesn't look very good. My problem is I don't want to clean up my office, so it looks like crap behind me. I think I need a clear color behind me to make this look good, but I will work on that and hopefully I'll get my face on future videos. So I think that's pretty much all I wanted to do for now. Analog output, beautiful sine wave, calculated and running with DMA. Now, if you ever want to start using the ADC, the input, it actually works exactly the same way as this. You create one of these channels, you clock it with the, we can show it, it's a little more complicated to set up. That will be another video. We might actually be able to use this output and feed it back into one of the inputs, but I will deal with that in a later video. I think this is enough for now. If you like this video, please like and subscribe. If you have any comments, positive or negative, as long as they're constructive, please put them down below in the comment, and I would love to hear back what you like and particularly what you don't like, so I can do better. This is still a learning experience for me, and I'm hopefully getting better. So that's it. Bye bye.